Crossing the North Atlantic in the year 1000 meant surviving waves taller than houses in an open, 60-foot wooden boat. The water temperature alone could kill a person in minutes. Success required specialized environmental engineering. Viking shipwrights spent weeks scouting dense, heavily shaded forests to select the perfect oak trees. Trees forced to compete for sparse sunlight grow incredibly slowly, producing wood with highly compressed, tight grain. Shipwrights carved this dense wood into thin, resilient planks. Instead of shattering under an ocean swell's kinetic energy, the overlapping hull planks flexed to absorb the impact. Mastering environmental properties, the Norse navigated to North America centuries before Columbus, landing on a coastline called Vinland. The Icelandic sagas explicitly document 5 separate voyages and multiple settlements in Vinland. Yet, in all of modern history, archaeologists have definitively confirmed only a single Norse site in North America. Validating that site, Lanso Meadows in Newfoundland, required absolute physical proof. Excavators found artifacts like these spindle whorls, essential tools for spinning wool that differed from indigenous technology. This satellite image reveals the geographic problem of finding a second site. The eastern coast of Canada contains thousands of miles of deeply indented, heavily forested, and rugged terrain. Archaeologists Dr. Sarah Parkak and her team abandoned the traditional method of digging random test pits. They shifted their methodology to high-resolution remote sensing from Earth's orbit. Locating microscopic traces of rotting wood and earth left behind 1,000 years ago meant expanding the search area from a single trench to thousands of square miles of orbital data. Scanning the entire eastern seaboard with specialized multispectral satellite imagery would cost tens of millions of dollars, a budget the team did not have. They developed a cost-effective workaround. Using open-access platforms like Google Earth to identify initial hotspots, they could purchase highly targeted 25-centimeter resolution aerial photographs from government mapping agencies for a fraction of the cost. The core scientific concept driving this orbital search is the detection of vegetation markers. When humans move Earth or build structures, the subsurface disturbance changes the nutrient and water distribution in the soil for centuries. Like furniture crushing a carpet, an ancient stone wall buried beneath the surface restricts water flow. Roots directly above are stunted, causing the surface vegetation to appear lighter or darker. By scrutinizing high-resolution aerial images for these microscopic shifts in plant color, the team identified distinct, rectilinear shapes at a specific peninsula called Point Rosee. A subtle variation in grass coloration, observed from the edge of space, initiated the first major ground expedition for Viking settlements in decades. Point Rosee sits at the southmost tip of Newfoundland, jutting into the wind-battered Gulf of St. Lawrence. Under Canadian archaeological regulations, researchers cannot simply arrive at a site and begin trenching based on a satellite photograph. They must first prove that a subsurface disruption exists. To gather this proof, the team relied on a magnetometer. A magnetometer is a highly sensitive instrument that measures minute variations in the Earth's natural magnetic field caused by human activity. Surveying the site required strapping the sensor to a researcher's back and hiking across the peninsula through 60-mile-per-hour winds. Imagery revealed a localized magnetic spike of positive 250, far exceeding the normal background readings. To the archaeologists, an extreme, concentrated magnetic anomaly of that magnitude indicated that something at those exact coordinates had been subjected to intense, intentional burning. With the subsurface disruption mapped, the team broke ground, transitioning from remote sensing to physical excavation directly over the magnetic spike. They uncovered an ovoid boulder sitting atop a small hollow ringed by stones, resembling an ancient hearth. Buried beneath that boulder lay 20 pounds of bubbled metal, identified by experts as roasted bog iron. This discovery matched the known chemistry of Norse metallurgy. Viking smiths could not throw raw, naturally occurring swamp iron directly into a blazing 1200-degree forge. Raw bog iron is saturated with water. Sudden extreme heat causes it to explode. To prevent this, the Norse gently roasted the ore at a lower temperature, baking out the moisture and leaving iron slag. The chemical and physical signature of the slag pulled from the dirt aligned with the Norse metallurgical techniques predicted by the satellite imagery and magnetic survey. Seeking to map the rest of the settlement, the team expanded their excavation to intersect the linear turf walls they had identified in the satellite data. The reality of the trench was disappointing. The walls were a complete illusion, a rare natural soil feature caused by water movement across the bedrock gradient that matched the dimensions of a human structure. With the structural evidence dissolved, the entire Point Rosee hypothesis now hinged on securing precise laboratory dates from the roasted rock and root samples collected at the hearth. Initial radiocarbon results provided a date range between 1255 and 1287 AD. However, that data was immediately contradicted by a tree root found directly below the surface, which dated to the 17th century. To break the tie, the team used advanced chronometric techniques, thermoluminescence, or TL, and optically stimulated luminescence, or OSL. Both methods measure the exact time a mineral was last subjected to high heat or exposed to sunlight. The OSL results delivered a confusing bombshell. The dates came back widely scattered, ranging from 791 AD to 1500 AD. There was no distinct, conclusive timeframe for the burning event. It is a lesson in the scientific method. When multiple, highly advanced datasets return a chaotic scattershot of conflicting information, a hypothesis cannot be confirmed. Evaluating the multi-year Point Rosee expedition requires checking the final evidence against the strict threshold of historical proof. The satellite anomalies, the intense magnetic spikes, and the physically confirmed roasted bog iron are real, but without cohesive chronometric dating or intact structural artifacts, the site remains officially unverified. This leaves two unprovable theories. Either indigenous Dorset groups possessed the capability to purposefully roast iron, or a Viking crew stopped at this inlet just long enough to smell a few nails for ship repairs before departing. Archaeology is not driven by the need to be right. Fieldwork is driven by curiosity and the discipline to accept ambiguous data without forcing a conclusion. Today, the harsh southern tip of Newfoundland remains a cold and beautiful mystery, its rugged coastal landscape largely undisturbed. While Point Rosee did not yield a confirmed longhouse, the integration of orbital satellites, magnetometry, and advanced luminescence testing, this integration provides a protocol for identifying ephemeral Viking Age outposts along the North American coast.